All right, now, buffer solutions. A buffer. The reason we call it a buffer is because it's a solution that withstands a change in pH. The reason it's able to do that is because you've got either a weak acid and its conjugate base, or a weak base and its conjugate acid. In other words, you have both acid and base in the solution. If you have both acid and base in the solution, what that means is that if you were to add a little bit of acid, you add a little bit of acid, it gets eaten up by the base, so the pH doesn't change a whole lot. If you add a little bit of base, it gets eaten up by the acid, so then the pH again is able to stay relatively stable. Let's look at an example. So, if we use the example of your chiku, your acetic acid, or your acetic acid, which is a weak acid, you put that in a solution with sodium acetate, which is going to contain the acetate ion, which is the conjugate base. Your buffer is going to consist of the CH3COOH, there's your weak acid, and it's also going to contain your CH3COO minus, which is your conjugate base. If you add a little bit of base, the OH minus of the base reacts with the acid and gives you your conjugate base, leaving you behind with some water. Whereas if you add some acid, it's going to react with the conjugate base and give you back the acid. Notice how they just swap what they produce. Of course, there's H2O on the end here as well. But you wind up having both of those substances being made by both of those reactions. So they essentially start replacing each other. They start replacing each other so that the overall pH, the overall amount of the acid with its conjugate base stays the same. And if the amount of the acid and the base stay the same, the pH is going to stay the same according to that Henderson-Hasselbalch equation again, which is on the previous page, but it's also down here. Right, so what actually happens is that your buffer neutralizes the added acid and or the base to produce the other partner in the conjugate pair. What I mean by the other partner is if you add base, the acid will turn into its conjugate base. If you add acid, the conjugate base will turn back into the conjugate acid. So you wind up just going back and forth so that you can keep the pH relatively constant. So if you want to find the pH of that buffer solution, we go back to our Henderson-Hasselbalch equation. If you mix some of the pH and if you mix some of the acid and some of the base, here's your ratio, right? Because your ratio in your Henderson-Hasselbalch equation needs your base, your conjugate base, and your conjugate acid. In this case, the base is your acetate ion, your CH3COO minus, and your HA, your acid, is your acetic acid, your CH3COOH. There's that ratio. So you know you added this much of the acid and you added this much of the salt that contains the conjugate base. Your ratio is built into the problem. So if you take your Ka, given the Ka, take the negative log of that, and your pKa, comes out to 4.74. You've got your pKa, 4.74, plus the log of the ratio of base to acid. But in this case, we've got 1.0 molar and 1.0 molar, so our ratio is 1 to 1. You take the log of 1, and you get 0, so this part drops out. So if the ratio is exactly the same, if the ratio of your acid and your base are the same, then the pH is going to be equal to your pKa, right? So when acid and its conjugate base are present in a 1-to-1 ratio, then the pH of that buffer is going to be equal to the pKa of the acid. Now, in some cases, you've got to be able to prepare a buffer that has a specific pH value. You need a specific pH value. So when you pick your pair, what you have to do is you have to find a pKa that has roughly that pH value. Because in order for it to be a buffer, you need approximately equal concentrations of the HA and the A-. You can't have one where there's too much of one and not enough of the other. So if you want to make a buffer of a specific pH value, you want to find an acid whose pKa is roughly equal to the pH that you're looking for. So for instance, if we wanted to make a buffer with a pH of 4.8, and our two options for our acids have a pKa of 4.87 or 2.12, we want to pick this one because it's going to give us a closer ratio of the two acid and base pairs compared to the other guy. We would need a ratio that's so far off balance that it wouldn't be a very good buffer, right? So what's going on is that when you make a buffer, you want the ratio to be roughly 1-to-1. So in other words, you want the concentration of your conjugate base to be about equal to the concentration of the acid. Therefore, you want a pH that's about equal to the pKa of the acid that you're going to use. So in this case, if we want a pH of 4.80, we're going to use an acid whose pKa was 4.87 because those are about the same. It's going to give us a much closer ratio. So now if we want to find the ratio we need, now you just plug in the pH, plug in the pKa of the acid into the Henderson-Hasselbalch equation again. So let's remind ourselves what that equation is. So our pH is equal to pKa plus the log of A minus the base divided by HA the acid. Sorry. So if you want to solve for this ratio, you plug in your pH, you plug in your acid, and then you just essentially solve for X. So if we've got 4.80, that's the pH we want, and we want a pKa of 4.87, we have to solve for the log of the ratio of A minus over HA. So when you solve this, our ratio of HA of the base to the acid, so we have our A minus over HA, comes out to, again, since these are all log base 10, to get rid of that log, we just do 10 to the 4.80 minus 4.87, which comes out to which comes out to 0.85. So in other words, you want a ratio where you have a bunch of the acid mixed with essentially 85% of that amount of the conjugate base. So you've got some of your acid, some of your base. Therefore, if you add any acid, the base is there to eat it up. If you add any base, the acid's there to eat it up, which allows that solution to maintain its pH, thus allowing it to act as a buffer.